14 hours. That's all that remains until we know the truth about 3I Atlas. 14 hours until an interstellar visitor from beyond our solar system reaches its closest point to the Sun, exposing itself to 33 gigawatts of raw stellar radiation. 14 hours until every telescope on this planet, every space probe in the inner solar system, every scientist who has staked their reputation on this object discovers whether they've been watching a comet or something else entirely. The clock is ticking, and the object hidden behind our Sun is not behaving the way it should. Tomorrow morning, at 11:47 Universal Time, 3I Atlas will reach Perihelion, its moment of truth, positioned precisely 1.36 astronomical units from the Sun, nestled between the orbits of Earth and Mars. At that moment, traveling at its maximum velocity of 68 kilometers per second, the object will be bombarded with more radiation than any natural comet from our solar system has ever been designed to withstand at that distance. The solar wind will tear at its surface. Photons will slam into its structure at the speed of light. Whatever this object truly is, tomorrow it cannot hide anymore. But here's what makes these final 14 hours so unbearably tense. The object is already showing us things that shouldn't be possible. Let me take you back 72 hours. Before 3I Atlas disappeared behind the Sun, telescopes at the Nordic Optical Telescope in the Canary Islands captured something that made astrophysicists around the world stop their work and stare at their screens. The comet's tail, that glowing stream of particles and gas that should always point away from the Sun, pushed outward by solar radiation pressure, had reversed direction. It was pointing toward the Sunday, not away, toward. This is what scientists call an anti-tail, a phenomenon that, while technically possible, under very specific geometric conditions involving viewing angles and orbital mechanics, should not persist. It should not strengthen. And it absolutely should not exhibit the characteristics that 3I Atlas demonstrated before vanishing from view. Professor Avi Loeb, director of the Institute for Theory and Computation at the Center for Astrophysics at Harvard, did not mince words about what this could mean. If the object were an alien spacecraft slowing down, and the anti-tail represented braking thrust, this shift from anti-tail to tail would be entirely expected. Braking thrust. Let those words settle for a moment. Not outgassing, not sublimation, not any natural process we associate with comets. Thrust. Controlled deceleration. The kind of maneuver you would execute if you wanted to remain in the solar system rather than pass through it on a hyperbolic escape trajectory. The establishment response came swiftly. NASA and the broader astronomical community explained the anti-tail as an optical illusion, a trick of perspective created by viewing geometry and the Sun's gravity bending the debris trail. Basic astronomical geometry, they said. Nothing to see here, just a rock behaving weirdly. But then came the nickel. On July 20th, barely 3 weeks after 3I Atlas was first detected by the Asteroid Terrestrial Impact Last Alert System in Chile, researchers using the Very Large Telescope detected something that should not exist. Nickel vapor, not trace amounts, not faint spectral lines that required extensive analysis to confirm. Substantial quantities of nickel vapor surrounding the object at a distance of 3.88 astronomical units from the Sunday. To understand why this discovery sent shockwaves through the astronomical community, you need to understand basic physics. Nickel has a boiling point of 2,913 degrees Celsius. At 3.88 AU, nearly 4 times the distance from Earth to the Sun, the temperature is far too cold for nickel to vaporize through normal sublimation. It shouldn't be there. It can't be there. Yet the spectroscopic data is undeniable. The team monitoring 3I Atlas watched as the nickel emissions intensified as the object approached the Sunday. They proposed that perhaps the nickel was bound in molecular structures that could release atoms when exposed to sunlight without requiring the extreme temperatures normally necessary for vaporization. A reasonable hypothesis. A scientific explanation that fits within known chemistry. Then came the compound analysis. Scientists detected nickel tetracarbonyl in the gas plume surrounding 3I Atlas. If you're not a chemist, let me explain why this discovery is profoundly disturbing. Nickel tetracarbonyl is a compound with the formula NiCO quarter. It forms when nickel reacts with carbon monoxide under specific conditions. And here's the critical detail. It is primarily known as an industrial compound used in human manufacturing processes, particularly in the purification of nickel through the Mond process. This is not a compound commonly associated with natural cosmic chemistry. This is industrial chemistry, manufacturing chemistry, the kind of chemistry that happens in refineries and industrial facilities, not in the vacuum of space around a natural comet. But wait, there's more, something even stranger. The spectroscopic analysis revealed that while nickel vapor was abundant, iron emissions were completely absent. In natural cosmic bodies, nickel and iron typically occur together. They're forged in the same stellar furnaces. They condense together in protoplanetary disks. They should be companions. Yet 3I Atlas shows nickel without iron, a chemical profile that suggests a separation mechanism, a refinement process, something that doesn't happen naturally in space. NASA's response to these discoveries has been conspicuously muted. While the space agency activated planetary defense systems through the International Asteroid Warning Network, officially this was framed as routine monitoring of a near-solar object. No public announcements, no press conferences, just quiet, intense observation. As the object exhibited what internal reports described as unexpected acceleration and anomalous behavioral patterns, the James Webb Space Telescope data added another layer to the mystery. The gas composition surrounding 3I Atlas shows far more carbon dioxide than water vapor, an uncommon ratio compared to typical comets from our solar system. Combined with the nickel findings, the iron absence, and the anti-tail behavior, the chemical profile of this object looks increasingly unlike anything we've classified as a natural comet. Now consider the timing, consider the trajectory, consider the precision. 3I Atlas was ejected from its home star system billions of years ago, traveling through the vast darkness of interstellar space. It crossed light years of void, navigated the gravitational influences of countless stars, and arrived in our solar system on a trajectory aligned almost perfectly with the ecliptic, the orbital plane, where all our planets circle the Sunday. The orbital inclination is just 5 degrees off, an alignment that astronomers describe as coincidental but remarkably convenient. The object passed within 0.19 AU of Mars on October 3rd. Tomorrow it reaches Perihelion between Earth and Mars. After Perihelion, it will pass 0.65 AU from Venus on November 3rd, then 1.8 AU from Earth on December 19th, and finally 0.36 AU from Jupiter on March 16th next year. This is not a random trajectory. This is a grand tour of the inner solar system, passing near every major terrestrial planet and approaching the largest gas giant before potentially departing forever. Unless it doesn't depart. Unless tomorrow's perihelion passage is not an exit, but a capture maneuver. Unless the anti-tail we observed was exactly what Loeb suggested, a braking burn designed to bleed off velocity and settle into a stable orbit. This is where we stand as the final 14 hours tick away. An object roughly 5 to 10 kilometers across, the size of Manhattan Island, composed of materials between 7 and 11 billion years old, making it potentially older than our entire solar system, approaches its moment of maximum exposure to solar radiation. An object that releases 330 pounds of material every second, with a composition of 87% carbon dioxide and 9% carbon monoxide, ratios that don't match our models of normal comets. An object that exhibits nickel vapor it shouldn't be able to produce, contains industrial compounds it shouldn't possess, lacks iron it should contain, and demonstrated a tail reversal that might be thrust exhaust. An object that Avi Loeb calls a potential black swan event, a term from statistical theory meaning an occurrence so rare and so impactful that it reshapes our entire framework of understanding. Tomorrow morning, 33 gigawatts of solar radiation will test this object's true nature. If it's a comet, we should see predictable outgassing, a symmetric coma, spectral lines matching known cometary compositions, and a trajectory that remains perfectly hyperbolic, carrying it out of the solar system forever. If it's something else, if it's artificial, if it's technological, the solar bombardment might trigger responses we cannot predict. Systems activating, course corrections, behaviors that no natural object would exhibit. Every major observatory on Earth is positioned and ready. ESA's ExoMars and Mars Express probes have already observed the object and will continue monitoring through Perihelion. NASA's space telescopes remain locked on the region of sky where 3I Atlas will emerge from behind the Sunday. The Hubble Space Telescope, the James Webb Space Telescope, ground-based facilities from Chile to Hawaii to the Canary Islands, all synchronized, all waiting for 11:47 Universal Time tomorrow. The scientific community is divided. Some researchers dismiss the anomalies as quirks of chemistry and physics operating under extreme conditions we rarely observe. They point to the anti-tail as a well-documented optical phenomenon. They suggest that the nickel emissions, while unusual, must have a natural explanation we simply haven't discovered yet. They argue that extraordinary claims require extraordinary evidence, and spectroscopic anomalies don't constitute proof of alien technology. Others are not so certain. The compound discoveries, particularly the nickel tetracarbonyl and the absence of iron, have no satisfactory natural explanation. The timing of the trajectory, while possibly coincidental, strains probability. The anti-tail behavior, lasting far longer than optical illusions typically persist, suggests real material movement rather than viewing geometry tricks. And the object's massive size, combined with its age and origin from the Milky Way's thick disk, makes it an object of profound interest, regardless of whether it's natural or artificial. This is not Oumuamua, the first interstellar visitor, which tumbled through the inner solar system in 2017, too faint and too fast for detailed analysis, leaving us with more questions than answers. This is not 2I Borisov, the second interstellar object in 2019, which behaved exactly like a normal comet and provided little controversy. This is something different. This is an object detected early enough for real-time monitoring, large enough for detailed spectroscopy, and strange enough that even conservative scientists admit its behavior defies easy categorization. The size alone is staggering. Between 5 and 10 kilometers in diameter, 3I Atlas is massive compared to typical comets. A comet of this size contains tremendous mass. We're talking about tens of billions of tons of material. If even a small fraction of that mass is composed of the unusual compounds detected, the nickel, the carbon monoxide, the mysteriously absent iron, then we're looking at a chemical inventory that challenges our understanding of how natural solar system bodies form and evolve. And here's a detail that keeps researchers up at night. The object is losing 330 pounds of material per second as it approaches the Sunday. Over the months since detection, that's thousands of tons of mass shed. Yet the nickel signatures strengthen. The unusual chemistry persists. Whatever is inside this object, beneath the surface layer being ablated away by solar radiation, the core composition remains anomalous. Loeb has been characteristically direct in his assessment. We cannot infer the true nature of 3 Atlas from the skin layer it has shed so far. Translation: what we're seeing is surface material. The real composition, the actual structure, remains hidden beneath. Tomorrow's perihelion, when solar radiation penetrates deeper, when 33 gigawatts of energy bombardment strips away more layers, might finally reveal what lies underneath. Consider what 33 gigawatts means. That's 33 billion watts of power concentrated on an object 10 kilometers across. To put that in perspective, a typical nuclear power plant generates about 1 gigawatt. We're talking about the energy output of 33 nuclear power plants focused on an area the size of Manhattan. If 3I Atlas is a natural comet, this bombardment will cause spectacular outgassing, potentially brightening the object significantly as ices sublimate and dust particles scatter sunlight. If it's something else, if there are materials beneath the surface that aren't ice, aren't rock, aren't any natural cometary component, tomorrow's radiation bath will expose them. The trajectory planning for tomorrow is extraordinary. ESA's Mars probes observed 3I Atlas as it passed the red planet earlier this month. Now, as the object reaches perihelion, multiple spacecraft are positioned for simultaneous multi-wavelength observations. Optical telescopes will track visible light. Infrared instruments will measure thermal emissions. Spectroscopes will analyze the chemical composition of any outgassing. Radio telescopes will listen for any electromagnetic emissions. This is the most comprehensive observation campaign ever mounted for an interstellar object, because we know this might be our only chance. If 3I Atlas truly is on a hyperbolic escape trajectory, if tomorrow's perihelion is just a gravitational slingshot accelerating it back into interstellar space, then this is goodbye. We'll watch it fade into the darkness beyond Neptune's orbit over the coming years. Another mystery we couldn't solve. Another question mark in the catalog of objects we've observed but never understood. But if Loeb is right, if the anti-tail was breaking thrust, if the object's trajectory adjusts after perihelion, if instead of accelerating outward it settles into an orbit that keeps it in the inner solar system, then everything changes. Then we're not watching a visitor pass through. We're watching something arrive. Something that traveled billions of years to get here. Something that might be trying to stay. The skeptics will say, this is speculation. That attributing intention to celestial mechanics is scientifically irresponsible. That we're seeing patterns where only chaos exists. They'll point out that humans have a long history of seeing intelligence in natural phenomena, from faces on Mars to signals from pulsars initially mistaken for alien beacons. They'll argue that parsimony demands we accept the simplest explanation, that 3I Atlas is merely an unusual but ultimately natural comet, and that all its anomalies will eventually be explained through physics and chemistry we already understand or will soon discover. And they might be right. Science advances through skepticism, through demanding rigorous proof before accepting extraordinary conclusions, through explaining phenomena using known laws before invoking unknown possibilities. But what if they're wrong? What if tomorrow, as 33 gigawatts of solar radiation bombard this object, as every telescope watches, as the scientific community holds its breath, something happens that cannot be explained by natural processes, What if the trajectory changes in ways that gravitational mechanics cannot account for? What if the spectroscopic data reveals materials that have no business existing in a natural comet? What if the object responds? The next 14 hours represent a threshold. We're standing at the edge of either confirmation or paradigm shift. Either 3I Atlas will behave exactly as a comet should, putting to rest all speculation about its nature, or it will do something that forces us to confront possibilities we've relegated to science fiction. Harvard astrophysicist Loeb has spent years arguing that we need to take the possibility of interstellar technology seriously, that the probability of intelligent civilizations arising somewhere in the billions of star systems across billions of years is not zero. That if even a tiny fraction of those civilizations develop the capability to send probes between stars, the galaxy might be full of artifacts we've simply failed to recognize because we weren't looking properly. His critics call him sensationalist. They say he jumps to alien explanations too quickly, that he's more interested in headlines than in careful scientific analysis. They point to Oumuamua, where Loeb proposed the object might be a light sail, an artificial structure using solar radiation pressure for propulsion, a hypothesis that generated enormous controversy and was largely rejected by the astronomical mainstream. But here's what his critics cannot dismiss: the data, the actual measurements, the spectroscopic observations of nickel tetracarbonyl, the absence of iron, the anti-tail lasting far longer than optical illusions should, the chemical composition that doesn't match natural comets, the timing, the trajectory, the precision of the orbital alignment. You can disagree with Loeb's interpretation. You can argue that there must be natural explanations we haven't considered, but you cannot argue with the facts that something about 3I Atlas is genuinely anomalous. That this object is not behaving like 2I Borisov behaved, that there are legitimate scientific mysteries here demanding answers. Tomorrow, we get those answers, or at least, we begin to get them. At 11:47 Universal Time, 3I Atlas reaches perihelion. The solar bombardment begins in earnest. Observations commence across every wavelength of the electromagnetic spectrum. Data streams in from dozens of facilities. Scientists analyze in real time, comparing observations to predictions, watching for deviations, monitoring for anything unexpected. If the object is natural, perihelion will be spectacular but scientifically straightforward. Outgassing will intensify. The coma will expand. We'll get excellent spectroscopic data on the composition. The trajectory will remain perfectly hyperbolic. Within days, as 3I Atlas emerges from behind the sun and becomes visible to telescopes again in December, we'll see a comet following exactly the path that Newtonian mechanics predicts, accelerating outward, leaving the solar system forever. If the object is artificial, all bets are off. We don't know what a technological artifact billions of years old would do when exposed to 33 gigawatts of solar radiation. We don't know if it would have automated systems triggered by solar proximity. We don't know if it would execute planned maneuvers at perihelion. We don't know if it would attempt communication. We don't know if it would simply continue its trajectory, a derelict from a civilization long extinct, or if something inside still functions, still responds, still acts with purpose. This uncertainty is what makes the next 14 hours so profoundly important. We're not just observing a comet. We're not just collecting data on an interstellar object. We're potentially witnessing first contact with evidence of intelligence beyond Earth. Or we're learning important lessons about cometary chemistry and physics. One of these outcomes is revolutionary. The other is valuable but conventional. Tomorrow, we discover which. The social media speculation has been intense. Doomsday theories trending alongside alien hypotheses. People asking if 3I Atlas represents a threat. if tomorrow's perihelion might somehow endanger Earth? The answer, unequivocally, is no. The object's trajectory keeps it 1.36 AU from the Sun at perihelion, and it will pass no closer than 1.8 AU from Earth in December, more than 269 million kilometers away. There is zero possibility of collision, zero possibility of gravitational disruption. The object poses no danger to our planet, but danger and importance are different concepts. 3. I-Atlas doesn't need to threaten us to be the most significant discovery in human history. If this object is artificial, if it represents technology from another civilization, the implications reshape everything we understand about our place in the universe. We would know definitively that we are not alone, that intelligence arises elsewhere, that somewhere, sometime, someone else looked up at their sky and wondered what was out there, just as we do, and that they built something that could cross the void between stars, something that could survive billions of years in the cold darkness of space, something that could navigate to other solar systems, something that might have a purpose we cannot yet comprehend. These are the stakes as the clock counts down. 14 hours until perihelion. 14 hours until 33 gigawatts of solar radiation test. The true nature of an object that has traveled farther and longer than anything humans have ever created. 14 hours until we know if we're watching a comet or witnessing something that will be remembered as the moment everything changed. The scientific instruments are ready. The observation protocols are finalized. The international collaboration is synchronized. Researchers from dozens of institutions across multiple continents are prepared to monitor, analyze, and interpret whatever happens tomorrow morning. Some are hoping for a straightforward answer. Confirmation that 3I Atlas, despite its anomalies, is ultimately a natural object. That the nickel can be explained. That the anti-tail was indeed an optical effect. That the chemical composition, while unusual, falls within the range of natural variation we simply hadn't observed before. These scientists want to solve the mysteries, but maintain the paradigm. To add fascinating new data to our understanding of interstellar objects without upending everything we think we know. Others are hoping for something more. They're hoping that tomorrow reveals evidence that demands we expand our thinking, that forces us to consider possibilities we've avoided. That opens doors we've kept closed because we lack the courage or the evidence to walk through them. These researchers see 3I Atlas as an opportunity, a chance to answer the oldest question humans have ever asked. Are we alone? Both groups will be watching at 11:47 Universal Time tomorrow. Both will see the same data. Both will analyze the same observations, but they might reach very different conclusions because scientific interpretation is never purely objective. We all bring our assumptions, our biases, our frameworks to the data. We see what we're prepared to see. The difference this time is that the observations will be so comprehensive, the data so extensive, that interpretation will be constrained by evidence to a degree rarely achieved in astronomy. We're not relying on a few images and limited spectroscopy like we did with Oumuamua. We have months of observations, multiple instruments, multi-wavelength coverage, international collaboration. Whatever happens tomorrow, we'll have the data to support rigorous conclusions. Unless the object does something so unexpected, so unprecedented, that our data collection protocols fail to capture it. Unless it executes maneuvers our instruments aren't designed to detect. Unless it operates on principles we haven't considered. This is the tail risk, the low probability but high impact scenario that keeps a small subset of researchers awake at night. The possibility that we're not prepared for what we might observe. But most likely, tomorrow will unfold according to one of two scenarios we've already considered. Either 3I Atlas is a comet, and perihelion will be spectacular but ultimately explainable, or it's something artificial, and the solar radiation will trigger observable responses that deviate from natural behavior. Either way, we'll learn something profound about the universe we inhabit. The final preparations are complete. The telescopes are aligned. The spectrographs are calibrated. The communication networks are tested. The analysis teams are briefed. Everything that can be done has been done. Now, we wait. 14 hours until we know. 14 hours until an object from beyond our solar system, carrying materials older than Earth itself, reaches the moment when it can no longer hide what it truly is. 14 hours until 33 gigawatts of solar radiation strip away the surface layers and expose the core beneath. 14 hours until humanity gets an answer to a question we've been asking since we first looked up at the night sky and saw lights moving among the stars. Are we alone? Or has something come from the darkness to visit us? Tomorrow at 11:47 Universal Time, we begin to find out. But first, we need to understand exactly what we're looking at. We need to trace the journey of 3I Atlas from its discovery to this moment. We need to examine every anomaly, every measurement, every observation that has brought us to these final hours before perihelion. We need to understand the science, the speculation, and the stakes, because what happens in 14 hours might be the most important observation humans have ever made. And we need to be ready to understand what we're seeing when the moment arrives. 33 billion tons. Let that number settle in your mind for a moment. Not 33 million, not 33,000. 33 billion tons of mass, traveling at 68 kilometers per second, approaching the sun on a trajectory so precise it passes near every major terrestrial planet in sequence. This is the revised mass calculation for 3I Atlas, determined by analyzing the object's gravitational acceleration and comparing it with the amount of material it sheds as gas and dust. To put this in perspective, 3I Atlas is 3 to 5 orders of magnitude more massive than Oumuamua, the first interstellar visitor, and significantly larger than 2I Borisov, the second interstellar object we've observed. The diameter of its solid density nucleus exceeds 5 kilometers, more than 3 miles across, larger than previous Hubble Space Telescope projections suggested. This is not a small rock tumbling through space. This is a mountain, potentially an entire range of mountains, forged in an alien star system billions of years ago and now hurtling through our cosmic neighborhood. Professor Avi Loeb calculated this mass by examining 3I Atlas's non-gravitational acceleration, the slight deviations from a purely gravitational trajectory caused by outgassing and other forces acting on the object. The result shocked even researchers prepared for surprises. The object's gravitational acceleration is less than 49 feet per day squared, an extraordinarily small value that implies tremendous mass. For an object to maintain such a stable trajectory while shedding 330 pounds of material every second, it must possess enormous inertia, mass so great that the forces pushing against it barely register. This discovery created what scientists are calling a major anomaly. Statistical probability suggests we should have detected thousands of smaller interstellar objects, objects the size of Oumuamua, before encountering something as massive as 3I Atlas. The fact that only 3 interstellar visitors have been identified, and the third is orders of magnitude larger than the first 2, violates our expectations about the size distribution of objects traveling between star systems. Either we've been extraordinarily lucky, catching one of the rarest classes of interstellar object during humanity's first few years of systematically searching for such visitors, or something about 3I Atlas makes it more detectable, more prominent, more significant than typical interstellar debris. The alternatives are equally intriguing and equally troubling for conventional explanations. But mass alone doesn't explain why 3I Atlas has captivated the scientific community. The trajectory, the precise orbital geometry, transforms this from an interesting discovery into a profound mystery. When 3I Atlas entered the inner solar system, it was traveling on what astronomers call a hyperbolic trajectory, a path that should carry it past the Sun and back into interstellar space without ever being captured into a closed orbit. The orbital eccentricity is 2.021, well above the threshold of 1 that separates bound orbits from escape trajectories. By every measure, this should be a flyby, a brief visit lasting months before the object accelerates outward beyond Neptune's orbit and disappears forever into the darkness between stars. But examine the trajectory more carefully. Look at the close approach distances. Look at the timing. On October 3rd, 3I Atlas passed within 0.19 astronomical units of Mars, close enough that ESA's Mars Express and ExoMars Trace Gas Orbiter could observe it in detail. The spacecraft, designed to photograph Mars from distances of hundreds to thousands of kilometers, successfully captured images of a comet 30 million kilometers away, a testament to both the skill of the operations teams and the brightness of 3I Atlas's coma. The observations revealed a coma measuring thousands of kilometers across, glowing as solar radiation caused the object to release gas and dust. The nucleus itself, just over 5 kilometers wide, remained unresolved, too small to distinguish from the surrounding haze at that distance. But the fact that Mars-orbiting spacecraft could observe an interstellar object at all represents an unprecedented opportunity, one that scientists immediately recognized and exploited. Tomorrow, October 29th at 11:47 UTC, 3I Atlas reaches perihelion at 1.36 AU from the Sun, positioned precisely between the orbits of Earth and Mars. Then, on November 3rd, just 5 days after perihelion, it passes 0.65 AU from Venus. On December 19th, it approaches to within 1.8 AU of Earth, still far beyond any danger zone, but close enough for detailed observation. Finally, on March 16th next year, the trajectory carries it within 0.36 AU of Jupiter, the solar system's largest planet. This sequence, Mars, Sun, Venus, Earth, Jupiter, reads like a planned itinerary. A grand tour of the inner solar system, visiting the major terrestrial planets before making a close approach to the gas giant that dominates the outer system's gravitational architecture. The orbital inclination of just 5 degrees off the ecliptic plane means 3I Atlas travels almost perfectly aligned with the planet's orbits, minimizing the vertical deviation that would be expected from a randomly oriented interstellar trajectory. Could this be coincidence? Absolutely. The galaxy contains hundreds of billions of stars, and countless objects have been ejected from their home systems over billions of years. Some fraction of those objects, purely by chance, will enter our solar system on trajectories that happen to align with the ecliptic. Some will, by random luck, pass near multiple planets. But here's where the statistics become uncomfortable. The probability of an interstellar object entering on a near-ecliptic trajectory is already low. The probability of it, then timing its arrival to pass near Mars, reach perihelion between Earth and Mars, approach Venus, pass relatively near Earth, and swing by Jupiter, all in the span of 6 months, represents compounding improbabilities. Not impossible, just increasingly unlikely with each additional coincidence we stack on top of the previous one. And then there's the Oberth maneuver possibility. In orbital mechanics, an Oberth maneuver exploits the fact that rockets are most efficient when they burn fuel at the highest possible velocity. By executing a thrust at perihelion, when an object is moving fastest due to gravitational acceleration near the Sun, even a small change in velocity produces a large change in orbital energy. This is how spacecraft maximize the efficiency of their propulsion systems when performing major trajectory changes. For a natural comet, this concept is irrelevant. Comets don't have propulsion systems. They don't execute planned burns. They follow gravitational trajectories modified only by the chaotic, unpredictable forces of outgassing. Unless they're not comets. If 3I Atlas were a technological artifact, if it possessed some form of propulsion system, perihelion would be the optimal moment to execute a major trajectory change. Loeb calculated the mechanics explicitly in his blog post analyzing this scenario. To adjust the orbital radius by 0.36 AU, enough to change from the current perihelion distance to Earth's orbital distance, would require altering the angular momentum per unit mass by approximately 0.36 AU multiplied by 68 kilometers per second, where 68 kilometers divided by s is 3I Atlas's velocity at perihelion. The amount of fuel required depends on the mass of the object executing the maneuver. For a small probe, a mini spacecraft ejected from a larger mothership, the fuel requirements would be manageable. For the entire 33 billion ton mass of 3I Atlas, the energy requirements would be astronomical, likely beyond any conceivable propulsion technology. But what if 3I Atlas isn't a single monolithic spacecraft? What if it's a carrier? A mothership designed to transport smaller probes across interstellar distances. The main body could continue on its hyperbolic trajectory, leaving the solar system as predicted, while smaller objects, equipped with their own propulsion, could separate and execute Oberth maneuvers at perihelion to alter their trajectories toward inner solar system destinations. This scenario, while speculative, addresses several puzzles simultaneously. It explains why the main body shows minimal, non-gravitational acceleration despite shedding material. The mass is too great for outgassing forces to significantly affect the trajectory. It provides a mechanism for smaller objects to reach Earth orbit within months after perihelion, the timeline Loeb calculated for a probe executing an optimal Oberth maneuver. It accounts for why we might observe trajectory deviations that don't match natural comet behavior. We'd be watching probe separation and independent maneuvering, not comet outgassing. And here's the critical detail that makes tomorrow so important. Any such maneuver would occur during perihelion when 3I Atlas is positioned behind the Sun from Earth's perspective, obscured by solar conjunction. Ground-based telescopes cannot observe objects too close to the Sun's apparent position. The glare overwhelms everything. Space-based assets have some capability, but solar conjunction represents a natural blind spot in our observational coverage. If something wanted to execute a major trajectory change without being observed in real time, perihelion during solar conjunction would be the perfect moment. We wouldn't see the maneuver happen. We would only discover it afterward, when 3I Atlas emerges from behind the Sun weeks later, and we can measure its post-perihelion trajectory. If the path has changed in ways that gravitational mechanics and outgassing cannot explain, we'll know something happened. But we won't have direct observations of the event itself. This is why scientists are positioning every available asset for tomorrow's observations. ESA's Mars Express and ExoMars Trace Gas Orbiter already observed 3I Atlas from their vantage point near Mars. ESA's JUICE mission, currently en route to Jupiter, will attempt observations in November using multiple instruments including cameras, spectrometers, and particle sensors. Coordination with NASA's Europa Clipper mission is being considered, particularly to observe using the twin ultraviolet spectrographs aboard both spacecraft. However, JUICE faces communication challenges. The spacecraft is currently close to the Sun and using its main high-gain antenna as a heat shield, relying on a smaller medium-gain antenna that transmits data at much lower rates. Additionally, JUICE is far from Earth on the other side of the Sun, further complicating data transmission. Scientists don't expect to receive data from JUICE's observations of 3I Atlas until February 2026, months after perihelion. This delay creates a frustrating gap between observation and analysis. Multiple spacecraft will collect data tomorrow and in the weeks following perihelion, but some of that data won't reach Earth for months, limiting our ability to conduct real-time analysis and coordinate follow-up observations. We'll have pieces of the puzzle arriving at different times, requiring patience and careful integration to construct a complete picture of what happened during 3I Atlas's closest approach to the Sunday. The Mars observations from early October already provided valuable data. Nick Thomas, principal investigator of the CASSS camera aboard ExoMars Trace Gas Orbiter, described the observations as extremely challenging, noting that the comet was 10,000 to 100,000 times fainter than the instrument's usual target, the brightly lit Martian surface. Yet the images clearly show the comet's coma, that fuzzy white dot moving against the background stars, comprising the nucleus and its surrounding cloud of gas and dust. The coma measured thousands of kilometers across, though the full size couldn't be determined because the brightness of the dust decreases rapidly with distance from the nucleus, causing the outer regions to fade into the image noise. The tail, which can extend millions of kilometers as comets approach the Sun, remained too dim for the Mars spacecraft to detect, though scientists anticipated it would become more visible in future observations as solar heating intensified. These Mars observations established an important baseline. We know what 3I Atlas looked like in early October, at approximately 3 AU from the Sunday. Tomorrow, at 1.36 AU, solar radiation will be significantly more intense. The coma should expand dramatically. Outgassing should accelerate. The tail should become prominent and bright. Any deviations from these predictions will be immediately noticeable and will demand explanation. But it's the chemical composition that continues to defy easy explanation. The nickel tetracarbonyl detection, combined with the absence of iron, creates a profile unlike any natural comet we've studied. Let's examine this in detail because the implications are profound. Nickel tetracarbonyl, Ni, co-quarter, forms when nickel metal reacts with carbon monoxide under specific conditions. On Earth, this reaction is exploited in the Mond process, an industrial technique for purifying nickel. Carbon monoxide gas is passed over impure nickel at moderate temperatures, forming volatile nickel tetracarbonyl that can be separated and then decomposed at higher temperatures to yield pure nickel. This is industrial chemistry, refined over decades to efficiently produce high-purity metal for manufacturing. The presence of this compound around 3I Atlas suggests that nickel and carbon monoxide are coming into contact under conditions that allow the reaction to proceed. But where is this happening? Natural comets contain ices, rock, and dust. They don't typically contain metallic nickel in a form that would readily react with carbon monoxide. They don't have the temperature and pressure conditions that favor nickel tetracarbonyl formation. Yet the spectroscopic signatures are clear. This compound exists in the gas surrounding 3I Atlas. The absence of iron deepens the mystery. In cosmic chemistry, nickel and iron are siblings. They form together in stellar nucleosynthesis. They condense together in cooling protoplanetary disks. Meteorites that fall to Earth typically show nickel-iron alloys, not pure nickel. The solar system's iron-to-nickel ratio is well established, and natural objects should reflect this ratio unless some process has separated the elements. What process separates nickel from iron in space? The Mond process does, because it specifically exploits the fact that nickel forms a volatile carbonyl compound, while iron's carbonyl is far less stable and more difficult to produce. If you wanted to extract nickel from a nickel-iron mixture, nickel tetracarbonyl formation is how you'd do it industrially. But we're not talking about a factory. We're talking about an object traveling through the vacuum of space, supposedly a natural comet from an alien star system. NASA's response to these findings has been conspicuously restrained. While the agency activated planetary defense protocols through the International Asteroid Warning Network, officially characterizing this as routine monitoring of a near-solar object, there have been no public press conferences, no detailed scientific briefings, no NASA TV specials explaining the discoveries to the public. Internal reports, according to sources cited in recent articles, describe 3I Atlas as exhibiting unexpected acceleration and anomalous behavioral patterns. What constitutes anomalous behavior for an interstellar comet? Outgassing is expected. Non-gravitational acceleration from jet forces is normal. Variation in brightness as the object rotates and different surface regions are exposed to sunlight is standard. What's not standard is acceleration that doesn't correlate with expected outgassing patterns. Direction changes that don't match comet jet models. Chemical signatures that resemble industrial processes rather than natural sublimation. The James Webb Space Telescope data revealed that the gas composition around 3I Atlas shows far more carbon dioxide than water vapor. For comets from our solar system, water ice is typically the dominant volatile, sublimating as the object approaches the sun and creating the characteristic comet coma and tail. Carbon dioxide is present, but usually as a secondary component. 3I Atlas inverts this ratio, showing a carbon dioxide-rich composition with relatively little water. This could be a clue to the object's origin. Different star systems form under different conditions. Protoplanetary disks with different chemical compositions would produce comets with different ice ratios. A comet from a carbon-rich system might naturally show elevated carbon dioxide compared to water. So this discovery, while unusual, doesn't necessarily imply anything artificial, but combined with the nickel tetracarbonyl, the iron absence, the anti-tail behavior, the precise trajectory, and the enormous mass, each anomaly adds weight to the question. Are we looking at a very unusual natural object, or are we seeing the fingerprints of technology? Professor Loeb has been careful to emphasize that 3I Atlas most likely is a natural comet, but he argues that the remote possibility of an Oberth maneuver must be considered seriously as a potential black swan event, a low probability scenario with huge implications for humanity. Black swan events in statistical terminology are outliers that carry extreme impact and are often rationalized after the fact as having been predictable, though they were not predicted in advance. If 3I Atlas were artificial, if tomorrow's perihelion involves probe deployment or trajectory changes indicating technological control, this would represent the ultimate black swan event. The discovery would instantly reshape human civilization's understanding of its place in the universe. Every assumption about our cosmic uniqueness would evaporate. Every question about whether we're alone would be answered definitively. Every field from philosophy to physics would need to incorporate the new reality that other intelligences exist and have achieved interstellar capability. The skeptics counter that extraordinary claims require extraordinary evidence, and spectroscopic anomalies plus trajectory coincidences do not constitute proof of alien technology. They're absolutely correct. Scientific rigor demands we exhaust natural explanations before invoking unprecedented scenarios. The history of astronomy is littered with premature claims of artificial phenomena, from canals on Mars to misidentified pulsars, all eventually explained through natural processes. But scientific rigor also demands we follow the evidence wherever it leads. If the data increasingly points toward phenomena that natural processes struggle to explain, if tomorrow's observations reveal behaviors that comets simply don't exhibit, then intellectual honesty requires we consider alternatives, even if those alternatives challenge our preconceptions. The debate within the scientific community reflects this tension. Some researchers view Loeb's suggestions about potential artificial origins as premature and sensationalist, arguing that he's pattern matching to extraordinary explanations before fully exploring ordinary possibilities. Others contend that refusing to seriously consider the artificial hypothesis, despite mounting anomalies, represents a different kind of bias, a reflexive conservatism that protects existing paradigms at the cost of potentially missing revolutionary discoveries. Both positions have merit. Science advances through a balance of open-minded exploration and rigorous skepticism. Too much skepticism, and we miss genuine breakthroughs. Too much open-mindedness, and we waste resources chasing phantoms. The art of scientific investigation lies in calibrating this balance appropriately for the available evidence. With 3I Atlas, the evidence is substantial enough to warrant serious consideration of multiple hypotheses. The natural comet hypothesis remains most probable based on prior experience, but the accumulating anomalies have elevated the artificial hypothesis from wild speculation to a testable alternative worth investigating. Tomorrow's Perihelion provides the test. 33 gigawatts of solar radiation will interact with 33 billion tons of mass, traveling at 68 kilometers per second. That interaction will reveal information about the object's composition, structure, and behavior that no other observation can provide. The solar bombardment will penetrate surface layers, expose subsurface materials, trigger outgassing from volatiles buried beneath the exterior crust, and potentially activate any systems designed to respond to solar proximity. If 3I Atlas is a comet, we'll see comet behavior, predictable, explicable, consistent with physics and chemistry we understand. If it's something else, tomorrow is when the mask comes off. The energy involved is staggering. 33 gigawatts represents 33 billion watts of power, the output of 33 large nuclear power plants focused on an area 10 kilometers across. This isn't gentle illumination. This is an assault of electromagnetic radiation across the entire spectrum, from radio waves to X-rays. Any ice on the surface will sublimate violently. Any volatile compounds will vaporize. Any structural weaknesses will be exposed as thermal stresses cycle the material through extreme temperature variations. For a natural comet, this is the moment of maximum activity. The brightness increases dramatically as outgassing accelerates. The tail can extend tens of millions of kilometers, swept back by solar wind and radiation pressure. Observations of comets at perihelion often capture spectacular displays as ices flash into gas and dust particles scatter sunlight. For a technological artifact, the implications are harder to predict. Would ancient alien technology be designed to withstand this radiation environment? Would it activate systems in response to solar energy? Would it deploy probes or execute maneuvers as part of a pre-programmed mission profile? We can only speculate because we have no experience with extraterrestrial engineering, but we can make reasonable inferences. Any civilization capable of sending probes across interstellar distances would need to account for the radiation environment around stars. Their spacecraft would need shielding, thermal management, and systems robust enough to function after billions of years in the cold vacuum of space, followed by sudden exposure to intense stellar radiation. They would likely design their mission profiles around perihelion, using the closest approach to the star as a key milestone for observations, communications, or maneuvers. If 3I Atlas were such a probe, tomorrow would be a critical moment in its mission, the moment when it confirms it has successfully reached the target star system, the moment when solar energy becomes available for power, the moment when maximum velocity allows efficient trajectory changes, the moment when the mission either continues to the next phase or, if the probe is defunct, simply passes through with no response. We're 12 hours away from finding out. 12 hours until the observations begin. 12 hours until the data starts streaming back from telescopes and spacecraft positioned around the solar system, all focused on one object, all measuring every wavelength, every emission line, every subtle change in position and velocity. The scientific teams are ready. Analysis protocols are established. Computer systems are prepared to handle the data volume. International communication networks will distribute observations in real time to research centers worldwide. This is global science operating at maximum coordination, a testament to how seriously the astronomical community is taking 3I Atlas, regardless of whether they believe it's natural or artificial. Because even if it's a comet, even if every anomaly has a natural explanation we simply haven't discovered yet, 3I Atlas represents an unprecedented opportunity. This is only the third interstellar object ever detected, and by far the largest and best observed. Everything we learn about its composition, structure, and behavior informs our understanding of how planetary systems form around other stars, what materials exist in interstellar space, and how objects are ejected from their home systems to wander the galaxy. And, if it's not a comet, if tomorrow reveals evidence of technology, of intelligence, of purpose behind the trajectory and the chemistry and the timing, then we're documenting the most important discovery humans have ever made. First contact, not with living aliens, but with the artifacts they sent to explore the cosmos long before we existed. The weight of this moment is extraordinary. 14 years ago, we had never detected a single interstellar object. Now, we're observing our third, and it's exhibiting behaviors that strain our explanatory frameworks. The pace of discovery is accelerating. Our detection capabilities improve each year. More telescopes come online. More sophisticated instruments deploy. The next few decades will likely see dozens, then hundreds of interstellar visitors identified and characterized. But 3I Atlas is special. It's the one that made us stop and truly question what we're seeing. The one that generated enough anomalies that even conservative scientists admit we need careful, comprehensive observations to understand what's happening. The one that has Avi Loeb, a Harvard professor who has staked considerable professional reputation on considering exotic possibilities, explicitly warning about black swan events and Oberth maneuvers. 12 hours from now, we begin to get answers. The countdown continues. The telescopes are aligned. The world watches, though most people don't yet realize how significant tomorrow might be. Because if 3I Atlas does something unexpected, if the observations reveal evidence that challenges the natural comet hypothesis, the news will spread rapidly and the questions will intensify. Are we alone? Or has something from the stars come to visit? Tomorrow morning at 11:47 Universal Time, the universe takes one step closer to showing us the answer. The sky will turn green, not across the entire planet, not a global phenomenon visible to anyone looking up, but for observers positioned correctly, with the right equipment trained on the precise coordinates where 3I Atlas will emerge from behind the sun in the coming weeks. There's a possibility that spectroscopic analysis will reveal the characteristic green glow of diatomic carbon, C2, a molecule common in comets but visually striking when concentrated in sufficient quantities. This green emission, if it appears, will confirm that despite all the anomalies, 3I Atlas is releasing carbon-based molecules in patterns recognizable from centuries of comet observations. Or it won't appear. And we'll need to explain why an object shedding 330 pounds of material per second, exhibiting a massive coma thousands of kilometers across, fails to produce the spectroscopic signatures every normal comet displays. Tomorrow at 11:47 Universal Time marks the Perihelion moment, but the real observations begin when 3I Atlas emerges from solar conjunction. The object entered conjunction on October 21st, 8 days before perihelion, positioning it directly behind the Sun from Earth's perspective. During these crucial days, while 33 gigawatts of solar radiation bombard the object at its closest approach, ground-based telescopes on Earth cannot observe it. The Sun's overwhelming glare makes observation impossible for instruments that rely on viewing angles more than 30 degrees from our star. This blind spot is not coincidental. It's geometry. Any object reaching perihelion between Earth's orbit and the Sun will necessarily pass behind the Sun from our perspective during the days surrounding closest approach. For natural comets, this represents a frustrating gap in observational coverage, but nothing more. For an artificial object executing planned maneuvers, this window provides cover during the most critical phase of a mission. NASA's Planetary Defense Coordination Office has explicitly stated that 3I Atlas gives researchers a real-world opportunity to test observation and modeling techniques for fast-moving interstellar objects. The activation of the International Asteroid Warning Network, the coordination of professional and amateur astronomers through specialized workshops scheduled before November 7th, and the explicit targeting of 3I Atlas for community astrometry campaigns signals how seriously the observing world is taking this object. Notice the careful language. Testing techniques, real-world opportunity, explicit targeting. These are not the phrases typically associated with routine comet observations. These are crisis management protocols, contingency planning frameworks activated when an object's behavior or trajectory demands heightened attention. The Planetary Defense Strategy, formalized through the United States government's national plan and implemented through NASA's standing playbook, operates on detection, characterization, and mitigation principles. Detection occurred on July 1st when Atlas Survey Telescope in Chile spotted an unusual object moving against the background stars. Characterization has been ongoing for 4 months, with every major telescope and space probe in position contributing data. Tomorrow begins the mitigation assessment phase, where researchers determine whether 3I Atlas poses any threat or requires any response beyond observation. But mitigation of what? The object's trajectory keeps it far from Earth. The closest approach occurs December 19th at 1.8 astronomical units, over 269 million kilometers away, absolutely no collision risk. Gravitational perturbations at that distance are negligible. If 3I Atlas exploded tomorrow, the debris would not threaten our planet. So why activate planetary defense protocols? Because the uncertainty isn't about physical danger, it's about the unknown. An object, exhibiting 8 documented anomalies earning a rank 4 on the Loeb scale, a classification system for rating the degree to which observations deviate from natural expectations, demands preparation for scenarios outside conventional frameworks. If tomorrow's observations reveal behaviors that cannot be explained through natural processes, the scientific community needs protocols in place for responding to information that reshapes our understanding of reality itself. Professor Loeb has been explicit about this. Even low probability events must be examined when the consequences could be profound. Planning and careful observation are crucial for both understanding and potential mitigation. Not mitigation of a collision threat, but mitigation of the societal, philosophical, and scientific implications if 3I Atlas proves to be artificial. Consider the timeline of what happens next. Tomorrow, October 29th, Perihelion occurs at 1.36 AU from the Sunday. The object remains behind the Sun from Earth's perspective, observable only by Mars-orbiting spacecraft and potentially by JUICE and Juno from their vantage points deeper in the solar system. Then, on November 3rd, just 5 days after perihelion, 3I Atlas passes approximately 97 million kilometers from Venus, about 60 million miles, a close encounter on cosmic scales, though far beyond any gravitational interaction that would affect either body. This Venus flyby allows researchers to observe how interstellar material responds to planetary gravity and solar heating. If 3I Atlas were executing an Oberth maneuver at perihelion, deploying smaller probes, or altering its trajectory through propulsion, the post-perihelion path past Venus would reveal these changes. The gravitational influence of Venus on 3I Atlas is calculable with extreme precision. Any deviation from the predicted path indicates forces beyond gravitation acting on the object. By mid-November, 3I Atlas emerges from behind the Sun, visible again from Earth just before sunrise. The comet will be moving through morning twilight, requiring observers to catch it low on the eastern horizon before the sun rises and drowns out everything in its glare. This is when ground-based facilities will get their first clear look at the object post-perihelion. The coma should be expanded from the intense solar heating. The tail should be prominent, swept back by solar wind. The spectroscopic signatures should show what materials were released during the perihelion bombardment. If the observations match predictions, if the chemistry looks like normal cometary outgassing, intensified by perihelion, but otherwise unremarkable, the natural comet hypothesis is confirmed. The anomalies, while interesting, would be classified as variations within natural processes we're still learning to understand. If the observations deviate from predictions, if the trajectory has changed in ways gravitational mechanics cannot explain, if the spectroscopic signatures show unexpected compounds or missing expected emissions, then the artificial hypothesis moves from speculation to serious consideration, requiring immediate investigation. By December 3I Atlas moves through the constellations Virgo and Leo. Growing dimmer as it recedes from the Sunday, brightness is expected to drop below apparent magnitude 12, at the threshold of what large amateur telescopes can detect. On December 19th, it makes its closest approach to Earth at 1.8 AU, still distant, but within range for detailed spectroscopy and trajectory measurements. This is humanity's best opportunity for comprehensive characterization before the object moves too far away for detailed observation. Then, in March 2026, 3I Atlas passes 0.36 AU from Jupiter, closer to the gas giant than Mercury orbits the Sunday. This encounter provides a natural experiment. Jupiter's immense gravity will measurably alter 3I Atlas's trajectory. The magnitude of that alteration depends entirely on the object's mass and velocity. By measuring how much Jupiter's gravity bends the path, researchers can independently verify the mass calculations derived from earlier non-gravitational acceleration studies. If the mass is indeed 33 billion tons, as Loeb calculated, Jupiter's gravitational influence will be specific and measurable. If the mass is different, if previous calculations were wrong, or if the object somehow shed significant mass during perihelion, the Jupiter flyby will reveal the discrepancy. This serves as a cross-check, a way to validate or refute one of the key anomalies that makes 3I Atlas so puzzling. After Jupiter, 3I, Atlas continues outward on its hyperbolic escape trajectory, assuming the trajectory remains hyperbolic. The orbital eccentricity of 2.021 places it firmly in the category of unbound orbits, paths that will carry the object out of the solar system forever unless some force alters that trajectory. Natural comets don't change from hyperbolic to elliptical orbits. They don't spontaneously decide to stay. Physics doesn't work that way, but propulsion does. A sufficiently large velocity change at perihelion, executed using the Oberth effect to maximize efficiency, could alter the orbital energy enough to transition from escape trajectory to captured orbit. The fuel requirements would be substantial, but for a probe that has traveled billions of years across interstellar space, that has presumably been designed for exactly this mission profile, those fuel requirements would have been anticipated and provisioned. This is the scenario that keeps Loeb writing blog posts and giving interviews despite the criticism from colleagues who view his speculation as premature. Not because he believes 3I Atlas is definitely artificial. He explicitly states it's most likely natural, but because the consequences of being wrong about dismissing the possibility are so profound that even a low probability scenario demands serious consideration. Imagine we're wrong. Imagine 3I Atlas is artificial, executes maneuvers at perihelion, deploys probes toward Earth, and we discover this only after the fact because we weren't looking for it, weren't prepared for it, had dismissed the possibility as too unlikely to warrant resources and attention. We would have failed at the most important observational opportunity in human history because we couldn't conceive that something so extraordinary might actually be happening. This is Loeb's argument. Not that 3I Atlas is aliens, but that we need to take the question seriously enough to observe comprehensively and analyze rigorously. That we need to prepare for the possibility even while acknowledging it's improbable. That black swan events, by definition, are things we don't expect until they happen, and then we recognize we should have been prepared. The scientific community is divided on whether this approach is prudent caution or wasteful sensationalism. Some researchers appreciate having someone willing to publicly discuss possibilities, others avoid for fear of ridicule. Science advances through creativity, through considering alternatives, through occasionally being wrong in productive ways that generate new lines of investigation. Others view Loeb's approach as damaging to astronomy's credibility. They argue that publicly speculating about alien probes before exhausting natural explanations gives ammunition to conspiracy theorists and makes it harder for working scientists to communicate about genuine uncertainties without being associated with fringe theories. They point out that Oumuamua, which Loeb famously suggested might be a light sail, was eventually explained through natural outgassing models, vindicating the skeptics who insisted on conventional explanations. But was Oumuamua fully explained? The debate continues. The outgassing models require assumptions about cometary composition and structure that remain unverified. The object tumbled in ways that don't match typical comet behavior. It exhibited acceleration that conventional physics struggles to explain without invoking specific, convenient conditions. The case is not as closed as the skeptics claim, nor as open as Loeb suggests. This is the context as we approach tomorrow's perihelion. Years of debate about how to interpret interstellar visitors. Decades of SETI searches that have found nothing despite examining thousands of star systems. Centuries of philosophical speculation about life elsewhere in the universe. And now, an object that exhibits just enough anomalies to make serious scientists pause and reconsider assumptions they thought were settled. The Legacy Survey of Space and Time, currently coming online in the Atacama Desert, will revolutionize interstellar object detection. The LSST will scan the entire southern hemisphere's sky almost every night, detecting objects far fainter than current surveys can spot. Predictions suggest the LSST might detect interstellar visitors monthly or even weekly once fully operational. Some will be dark like Oumuamua. Some will be bright with tails like 2I Borisov. And some might be like 3I Atlas, large, anomalous, challenging to categorize. This means 3I Atlas is not just a singular mystery. It's the beginning of a new era where interstellar objects become routine discoveries rather than rare events. Each new detection will be compared against 3I Atlas. Each anomaly will be evaluated in context of what we learned here. The frameworks we develop now for thinking about these objects will shape how we interpret future discoveries. If we dismiss 3I Atlas's anomalies too quickly, if we force-fit observations into conventional explanations without rigorously testing alternatives, we risk missing patterns that might emerge across multiple interstellar visitors. If we overinterpret every unusual observation as potential evidence of technology, we risk crying wolf so often that real signals get lost in noise. The balance is difficult. Science requires skepticism, but not closed-mindedness. Open-mindedness, but not gullibility. The ability to hold multiple hypotheses simultaneously while waiting for evidence to distinguish between them. Tomorrow's perihelion is that evidence collection moment. Multiple spacecraft positioned throughout the solar system will observe simultaneously. JUICE, despite communication challenges and the need to use its high-gain antenna as a heat shield, will attempt observations in November once thermal conditions permit. The data won't reach Earth until February 2026, but it will provide a different vantage point than any ground-based facility can offer. NASA's Juno spacecraft, currently orbiting Jupiter, might have been capable of intercepting 3I Atlas under ideal conditions, simulations suggest, though no such mission was attempted. The missed opportunity highlights both the rarity of interstellar visitors and the challenges of responding quickly when they appear. We detect these objects months before perihelion, at best, not years. We have limited time to plan observations, let alone missions. Europa Clipper, NASA's newest spacecraft en route to Jupiter, might coordinate ultraviolet spectrograph observations with JUICE. The synchronization of multiple spacecraft using different instruments observing from different positions creates a comprehensive dataset impossible to achieve with any single facility. This is how modern astronomy operates at its best. International collaboration, leveraging every available asset to maximize scientific return. The specialized workshop scheduled before November 7th will train both professional and amateur astronomers in advanced astrometric methods for accurate data collection. Amateur astronomers have become critical contributors to time domain astronomy, monitoring objects that professional facilities cannot observe continuously. Their measurements of 3I Atlas post-perihelion will help refine the trajectory, detect any unexpected deviations, and provide redundant observations that professional facilities can compare against their own data. This community astrometry campaign represents science operating as a collective enterprise. Not just elite institutions with billion-dollar telescopes, but thousands of observers worldwide with modest equipment contributing their measurements to a shared understanding of what we're seeing. Because ultimately, this is a shared question. Are we alone? The answer, whether yes or no, belongs to all of humanity, not just to astronomers and astrophysicists. If 3I Atlas is natural, we learn more about the diversity of objects traveling between stars and the conditions that exist in other planetary systems. Valuable science, expanding knowledge, but within familiar frameworks. If 3I Atlas is artificial, everything changes. Every person on this planet wakes up to a universe where intelligence has arisen elsewhere, where technology exists beyond Earth, where something or someone looked up at their sky, wondered what was out there, and built machines capable of crossing the void to find out. The implications cascade across every domain of human thought. Philosophy must grapple with our place in a universe where we're not unique. Religion must contextualize teachings within a cosmos inhabited by other intelligences. Science must incorporate the reality of technological civilizations into models of cosmic evolution. International relations must consider how humanity responds to information that transcends national boundaries and earthly politics. But we're getting ahead of ourselves. Tomorrow is not first contact. Tomorrow is data collection. Tomorrow is observation, measurement, spectroscopy, astrometry, photometry, all the technical tools astronomy has developed over centuries applied to one object during its moment of maximum exposure. The results will not be immediate. Data requires analysis. Observations need verification. Measurements demand calibration and cross-checking. The comprehensive picture of what happened at Perihelion will emerge over weeks and months as researchers integrate observations from multiple facilities, compare against predictions, and test different hypotheses against the evidence. By late November, when 3I Atlas is visible from Earth again, we'll have preliminary results. The trajectory will be measured precisely enough to detect any deviations from purely gravitational motion. The spectroscopy will reveal what materials were released during perihelion. The brightness curve will show how solar radiation affected the object's activity. By December, as 3I Atlas makes its closest approach to Earth, the analysis will be refined. Papers will be submitted to journals. Conferences will be scheduled. Debates will intensify as different research groups interpret the same data in different ways, which is how science advances, through productive disagreement constrained by evidence. By March 2026, after the Jupiter flyby, we'll have independent mass confirmation. The object's response to Jupiter's gravity will either validate or refute the 33 billion ton calculation that created the major anomaly designation. This cross-check is critical because mass drives so many other interpretations. If the mass is wrong, cascading conclusions need revision. And throughout all of this, JUICE's delayed data will still be in transit, not arriving until February 2026. Those observations, made from a unique vantage point during perihelion when Earth-based facilities couldn't observe, might contain critical information that changes interpretation of earlier results. The delayed gratification is frustrating but unavoidable, given the realities of spacecraft communication and thermal constraints. This is the timeline we face. Not immediate answers, not tomorrow's perihelion providing instant clarity, but a months-long process of observation, analysis, debate, and refinement, until we understand what 3I Atlas truly is. Some questions will be answered definitively. The trajectory will be measured precisely. The composition will be characterized comprehensively. The mass will be verified through Jupiter's gravitational influence. These are empirical questions with empirical answers. Other questions may remain ambiguous. Is the nickel tetracarbonyl signature conclusive proof of industrial chemistry? Or could natural processes we haven't considered produce the same compound? Is the anti-tail behavior explained by viewing geometry, or does it suggest thrust? Is the orbital alignment coincidental, or statistically improbable enough to warrant concern? Science doesn't always provide clean answers. Sometimes the data supports multiple interpretations. Sometimes uncertainty persists despite comprehensive observations. Sometimes we need to wait for the next interstellar visitor to provide comparative context before understanding the first one. But tomorrow, we take the first step. Tomorrow, 33 gigawatts of solar radiation interact with 33 billion tons of interstellar material traveling at 68 kilometers per second through its closest approach to our Sunday. Tomorrow, every telescope that can observe will be watching. Tomorrow, the scientific community holds its breath and waits to see what the universe shows us. 14 hours from now, the countdown ends. 14 hours from now, Perihelion occurs. 14 hours from now, humanity gets the most comprehensive look at an interstellar visitor we've ever attempted. And in the weeks that follow, as data arrives and analysis proceeds, we'll discover whether 3I Atlas is a very unusual comet teaching us new physics and chemistry, or whether it's something else entirely, something that demands we reconsider everything we thought we knew about our place in the cosmos. The telescopes are ready, the spacecraft are positioned, the observation protocols are finalized, the international coordination is synchronized. The scientific community is prepared to observe, measure, and analyze whatever tomorrow reveals. Some researchers expect confirmation that, despite its anomalies, 3I Atlas is natural. Others hope for observations that expand our frameworks and force us to consider alternatives. Both groups will see the same data. Both will analyze using the same physics. But they might reach different conclusions, at least initially, until the weight of evidence tips the scales decisively one direction or the other. This is how science works. Not through instant revelation, but through careful accumulation of evidence, rigorous testing of hypotheses, and honest acknowledgement of uncertainty when warranted. Tomorrow begins that process for 3I Atlas. The object has traveled billions of years to reach this moment. It has crossed light years of interstellar void, navigated the gravitational influences of countless stars, and arrived in our solar system during the brief historical window when humanity possesses the technology to observe it comprehensively. Whether that timing is coincidence or something more, we may never know with certainty, but we'll know more tomorrow than we know today, and more next week than tomorrow. And by the time 3I Atlas fades from view beyond Jupiter's orbit, heading back into the darkness between stars, we'll understand what visited us during these remarkable months when an object from beyond challenged us to look up, pay attention, and ask the questions that matter most. Are we alone? Or has something come from the stars to show us we're part of a larger cosmic community? Tomorrow, at 11:47 Universal Time, as 3I Atlas reaches perihelion and 33 gigawatts of solar radiation test its true nature, we take the next step toward answering that question. The countdown continues. The moment approaches. The universe prepares to reveal a piece of its deepest secret. And humanity watches, waits, and wonders what tomorrow will bring. 14 hours until perihelion. 14 hours until we know. 14 hours until the most important observation any of us will ever witness begins. The final countdown has begun.